pick on a bit of information you guys already know. What percent of bell-shaped data is between, let's do a quick little recap here. And I want to show you how what we already know ties to this curve. What percent of bell-shaped data is between -1 and 1 on this curve? We would call that back in the day within one standard deviation. Yes, and you know the answer, don't you? What is the answer? Approximately what percent? Be brave.
90.
Within one standard deviation.
68.
Just about 2/3, 68%-ish, 68, yes?
68.
It's one of those numbers we've been using for a few weeks now. Now, we got it back in the day by empirically counting. I gave you bell-shaped data, and we empirically counted the data in the curve and said, oh, it's about 68%. It comes out to be about 68% over time. So we know the answer to this. Call this letter A, I guess. We know the answer is about 68%. What I'd like to do is explain to you mathematically how that number is arrived at. Besides counting data, I mean, that's one way to do it, is just to count the data. The way mathematicians do this is they actually add up the probabilities on this curve. Now you're going to say to me, how the hell can you do that? Because how many of them are there?
It's infinite.
There's infinite. So here's what mathematicians do. -1 is the first one. So they add that one up, whatever that one's equal to. And it's not important to know what that one particular is equal. It is equal to something, but it's not worth viewing in isolation. It's only worth viewing when it's added with other ones. And then mathematicians go, oh, I can also get 0, that's an easy one. And I can also get 1, that's an easy one. Give me some other number in that range.
2.
2's outside, right?
Yeah.
0.5?
0.5.
Give me another one. 0.75. Give me another one.
0.25.
Give me another one.
-0.8.
Very nice. Give me a touche. Give me another one. This gets a little bit old, doesn't it?
0.233.
Good, good. So what we've done is, what mathematicians will do is they'll put a few of them up like that, and then they'll draw, now don't do this in your notes, they'll draw rectangles off of each one that are uniformly sized. So for example, this one right here, they'll draw a rectangle that's a slight bit to the right, a slight bit to the left, and then drop in the rectangle like this, and they'll calculate the area of that rectangle. And you see what just happened? It missed a little bit up top here, and it was a little bit outside here, and they say, ah, it's a wash. Now that doesn't sound very mathematical, does it? Ah, it's a wash. 2. I mean, that's not how mathematics is done, right? So what they do is, they make that rectangle narrower and narrower and narrower. And the more narrow you make it, the less off it is, correct? Now clearly, the best rectangle would be one that is infinitely thin. But what ends up happening then is, with infinitely thin rectangles, is essentially you just do this. And the next thing you've done is, you've shaded every single possible value from -1 to 1 with infinitely thin rectangles. Congratulations, in 3.5 minutes, you just got Math 252. That is called integral calculus. The idea of, say that again.
241, isn't it?
It is part of 241 as well. Yes, you took 241, Linda. It is part of 241. But 252, the entire course of Math 252 is devoted to the study of what I just described. At its simplest form, that is what integration is in calculus. You don't have to do integration in this classroom because calculus was not a prerequisite for this course. But that is what has to be done to get any degree of precision on that estimate. If you try to use rectangles that are too big, you've got too much error. So for example, suppose we go a half a unit off of each of the numbers. -1, down and up a half. Well, if you do that, it's going to look like this.
Yeah.
Right? And now you're missing quite a bit, yes? You've got some dead space in here, you've got some extra space out here, dead space, extra space, dead space. So you keep shrinking and shrinking and shrinking and shrinking. And calculus allows you to let it shrink off to infinity. I mean, and what's cool is you can shrink off to infinity without actually having to go to infinity. Because number systems begin to behave certain ways if you can analyze the functions. I'm going to stop talking about it because you all look very scared right now. And that's not the point of today, was not to scare you. The point is that you can get this done without having to do the calculus because I've written a program that does it for you automatically. So you already know that this is 68%. That's how it's actually legitimately calculated, by doing the shading. Hey, what percent is within 2 standard deviations? How about within 2 standard deviations? Which would be between -2 and 2. What's that number? You know this one too, don't you? What percent of the data in bell-shaped data is between -2 and 2? Yes! So here, shading all the way across, shading all the way to here, that's 95%. That's a very special number of statistics for a lot of reasons. That's 95%. Now what's cool about this is, what percent is between -2 and 1? What percent is this little red piece right here? Could we figure that out now? Could we figure that out? I think we can. Say that again. Be brave. Be brave.
7%.
Johnny, why is it 27%?
Because it's in between 68.
Oh, careful. One more thing to do. So this is 68, right? And this is 95. And you do the difference of that. 95 minus 28, no, minus 68 is 27. But that's both of these, isn't it?
Oh.
So this would be half of that, yes? 13 and a half? 13 and a half? So outside of the first standard deviation, but below the second, there could be 13.5%. Now that's something I never made you do before in 243 because it didn't make any sense at the time. Now it makes perfect sense because now we can start. Those would be people with the higher IQs. Between the first and second standard deviation above average. Ooh, that's good. That's very good. That's very good. Fair-ish? Maybe. Getting there. Can we go out even further to 3? Yes, we can. But I think we should be done drawing on this curve. Not that I don't want to stop drawing curves, but I'm tired of drawing the areas on this curve, and you should be too, because it's too tedious. If you're not going to add the rectangles up, FYI, if you're interested in a more mathematical look at what I just did, I posted some enrichment stuff on the website for you. Of course, you don't have to look at it at all if you don't want to, because it's calculus-based, and you can look at it if you want to. But the reason I wrote Stonormal, which is a program in your TIs, is I want you to not have to do that. I want it to do the adding for you, and you work on the interpretation. Let's take 5. We're getting that glazed look. Let's take 5. We'll come back and show you how to use your TIs. Yes?